In this video, we'll take a look at some of the tricky problems in Chapter 10. Okay, so first I want to start out by looking at question 12. So this one says, a person claims to be able to predict the outcome of flipping a coin. So they basically flip the coin 25 times and he's correct 16 of those 25 times. So just on the face of it, I mean, that's better than 50-50. But we really only have one trial, so we can generate a confidence interval to see if this is compelling enough. Let's put it that way. All right, so we're going to compute a 95% confidence interval on the proportion of times this person can predict the coin flips correctly. And then we're going to interpret what that confidence interval means. All right, so first of all, we need to convert this fraction into a proportion. So 16 divided by 25 should give you 0.64. And then this is 25 trials. All right, so as you guys probably learned by working through these problems, confidence intervals always involve a statistic of some sort, plus or minus a critical value times a standard error. Now, in this example, the critical value is going to be from the normal distribution because we use that to approximate what's going on with proportions. And then the other thing about proportions that make them a little different is that we have to add and subtract a correction because they're prone to the same kinds of errors that we saw in other approximations using normal approximations of binomials, for example. Because this data that you're looking at here, this definitely has a binomial distribution. But you can't use the binomial distribution to generate a confidence interval, so we have to use this formula. Okay. All right, so the statistic then, in this case, is the 0.64. So that's an estimate, right? That's a point estimate of how good this person is at predicting the outcome of a coin flip. All right, and that's just based on 95. Okay, so what we're going to do is we're going to add and subtract the critical value. So on a normal distribution, the critical value is 1.96. And then we multiply that times the standard error. Now, for a proportion, remember that the standard error is the proportion times 1 minus the proportion divided by 25. So that's what we have here in parentheses. You sort of do all that and then take the square root of it. And then the correction is 0.5 over n. Okay? And this time n is 25. All right? So I'll let you plug all that into a calculator on your own. I think you should be able to handle that part of it. But this is the confidence interval that you get. Now, we didn't talk a whole lot about how you interpret things like this, but you got to remember that the mean of the what we call the population mean, in this case it's this person's ability, if he tried to run this over and over and over, like doing the same 25 flips of the coin, the population mean is going to be in this confidence interval about 95% of the time. That's what it means. And as you can see, 0.5 is in here, which is 50-50. So, in fact, so are some things below 0.5. So, since it's, 0.5 is actually within the confidence interval, we shouldn't conclude that this guy is good at predicting, the outcome of the coin toss. He was just lucky, or may have just been lucky. Now, we don't know for sure, right? Because this is just a confidence interval. I mean, he may be able to predict the outcome, but this is not strong evidence of that. Now, how would we get strong evidence? Well, one thing we could do is we could try and increase the sample size and then see, we'd have to run the whole experiment again. In other words, instead of flipping the coin 25 times, we could try flipping the coin 100 times and see how well this guy performs. But you can't really do anything else with this at this point. All we can do is look at the data that we have and say, well, 0.5 is in the confidence interval. Therefore, we can't really say that he can predict the outcome. Now, what if it wasn't? Like, what if the lower limit was 0.6? Then you'd say, yeah, this guy can predict the outcome. All right. So that's 1012. All right, let's take a look at 1014. So this is one that students frequently have trouble with. Okay, so let's see what we've got here. So we have a confidence interval for a population mean is computed for an n of 16. Okay, ranges from 12 to 28. Okay, so we've got the confidence interval and we have the sample size. But all those other things that go into computing the confidence interval, we don't have those here. So we're going to have to figure out how we can get them. Okay, let's continue though. So we're going to do a new experiment, all right, and we're going to make 36 observations. Okay. So we can't really know what's going to happen in the new experiment because it, depends on a random sample, coming out of the population. But even so, we should be able to predict kind of our best estimate of what it is. All right, so let's take a look at this. Okay, so first of all, I want to point out one thing about this question that makes it a little bit incomplete. So Lane does not tell us if the population standard deviation is known. But if you were to look at his key, you're going to see that he worked this problem as though the population standard deviation is known. Now, we'll work it that way, and then we'll look back of it and maybe ask, well, what would we do if it wasn't known? Because we could still do it, even if the population is not known, but we'd have to be a little more careful about how we did it. All right, well, first of all, remember that a confidence interval around a mean is the mean plus or minus the critical value times the standard error. And then I'm sure you know by now that the standard error is the population standard deviation over the square root of n, when this is known. Okay, so which of these variables do we know? Well, not many of them. We know n. So we got to figure out, well, how do we get the other ones? Well, remember that in a confidence interval, the mean is always right in the middle, okay? So we can find what the mean is. Okay, so the mean is in the middle of the confidence interval. So if you have 12 to 28 as the confidence interval, can you see that if you subtract 12 from 28, you get 16? So half of that would be 8, right? And if we add 8 to the lower number, 12, that means that 20 is right in the middle. In other words, you have 8 on either side of it. So that has to be the mean. Okay, so now we've got this. Now the critical value, we know that, right? Because that's got to be 1.96 if it's a 95% confidence interval. Oh, he doesn't say that either. But that's another thing that should be said. This should say this confidence interval is a 95% confidence interval. Well, we're going to treat it that way. All right, and then what else do we have? We have n, but we don't know the standard deviation. Okay, so we should be able to find that, though. What we can do is we can fill in what we know. All right, so rewriting this formula to get the upper value, so we've got the upper value is 28. The only way to get that would be to take the mean plus the critical value, all right, times the standard error, which is the standard deviation over the square root of 16. So now we've got a formula here that only has a single variable in it, and we can find that variable through some simple algebra. So first thing I would do is subtract 20 from both sides, right? That gives you 8 on this side. And then, if you take the square root of that, it's 4. So 4 times 8, cross multiplying 32, divide both sides by 1.96. There's the what the standard deviation is. Now we can you can go ahead and solve that if you want, but it may be easier to just take that and put it into the new formula. Okay, so what we want now is we want to make a new formula, all right, or a new confidence interval, and we're going to use the same thing. The only thing is that the sample size is going to be different. So we're going to be up to 36. So we're going to use the same thing where the mean doesn't change because it's the same population. So that's 20. Critical value, that doesn't change. That's 1.96. How about the standard error? Well, now we know what the population standard deviation is. We found that here, and we know what n is because that's what is given in the question. So now we can get the entire new confidence interval. So set up a new one. All right. It would be 20 plus or minus the critical value times here's that population standard deviation divided by the square root of n. Okay. So you solve that, and you will get exactly the same answer that Lane has in the guide. All right? Okay, now I want to take a look at a couple of the case studies, and then we'll look at one more question that comes from the artist website. Okay, so we're going to look at the ADHD study. Now, one of the reasons why I want to do this is because I want to show you guys again how to use PASS to get some of these answers and how to work with Excel spreadsheets. I don't think these are particularly hard, but we'll go ahead and do it. Okay, so what is the correlation between the participants' correct number of responses after taking the placebo and their correct number of responses after taking 60 milligrams per kilogram of MPH? Okay, so I've already downloaded this data set. Hold on, let me see if I can find it here. Here we go, ADHD. Okay, all right, so I guess DO is the placebo and D60 is the one. And we want to look at a correlation. So apparently these are the same individuals that were treated under these two experimental conditions. So just to make my life easier, what I'm going to do is I'm going to select these two middle things that we're not interested in, and I'm going to remove them. So you can just, hit delete over here is probably fine. Okay, now this, we want to look for a correlation between these. So I'm going to select all this. All right. Now, notice that we've got the title up here, so we want to be careful when we paste it into PASS that goes into the column attributes and not as a data point. All right, let me just close all these other windows so we can get to PASS here. All right, so here we have PASS. So we're going to select column attributes. You select this cell right here, hit Control V, and notice how we pasted those two things in. So now we can get a correlation coefficient by selecting the two columns, and then we go to Model, Linear, Bivariate. Hold on, Model, Linear, goodness, come on, Bivariate. Okay, and let's see. So correlation coefficient is over here. All right, so here we have a correlation coefficient. Now, you may notice there are some confidence intervals up here, but those are for slopes and intercepts of regression lines. We're going to be talking about those later in the semester, so for now, just ignore those things. You're not going to find the answer you need here. We have to still calculate the answer the old way. All right, so that's what we need there, 0.7998, all right? Now, there's a couple of different ways you can put that somewhere. You can copy the whole thing if you want, just by hitting copy, and you can paste it, or we can just type it into our spreadsheet, and I think that's what I'm going to do because it'll just make things a little easier. All right, so I'm going to put a little space here. I think I'll work the rest of this in the spreadsheet. Hold on, let me slide this thing over again. Try that again. Okay, there we go. All right, so R is 0.7998. Okay, that's the correlation coefficient. All right, now remember the first step is that we have to convert that to Fisher's Z. So I'm going to put the Z values over on this side. All right, so let's see here. Actually, you know what? I'll even label things so we can see what we've got here. All right, so here we'll put R. All right, and over here we'll put Z, so Fisher Z values. All right, so let's first go into past. I'm sorry, not past. Lane's calculator here. All right, so let's see. Let's find the calculators. And we need Fisher Z. There it is. All right. So 0.7. Let's see. Now I'm already forgetting what it was. All right. 0.7998. Let's see. I think all that'll fit in here. 0.7998. Okay. All right. So there's the Z prime value, or Fisher Z value. All right, now that has a normal distribution. So I'm just going to hit Control Copy so I don't have to remember what it is. Not that, that's not the right sheet we want here. Where is this one? Oh yeah, we put it up here. Okay, so that goes here. Okay. All right, now remember to find the upper value. What we need is a standard error. Okay, so I'm going to write the standard error right here. All right, we'll put SE just so we don't have to keep messing around with it too much. Okay, so how many of these do we have? Looks like 24 individuals, because notice DO's in the beginning here, so there's 24. Okay, remember the standard error is really easy. So it's just equal to the square root. Let's see. No. 1 over square root of n minus 3. So 24 minus 3 is 21, right? Okay. So that should be the standard error. All right. Now, let's see. So to get the upper limit, okay, remember we're going to take this value, we're going to add it to critical value times that standard error. So that's going to be equal to, looks like we've got E2, all right, plus 1.96, all right, star C2. Yeah, okay. That should give us our upper Z value, okay? Now the lower Z value, we just subtract those two things. So this is equal to E2, all right, minus 1.96, all right, star C2. Okay. Let's see, I think I was supposed to put some parentheses in there, otherwise it's not going to work. Okay. All right. Did I remember to do that up there? No. Better double check this. I might have worked, but maybe it didn't. Let's see. I think it probably did. Okay, yeah. All right, so it didn't change anything. Okay, now, we're not done yet because we want a confidence interval around the correlation coefficient. Okay, so these are the z-scores. So now we have to convert those to R. All right, so we go back over here. And again, you can kind of use, copy paste so you don't lose like decimals and things like that. So I'm going to start out, I'm going to hit a Control Copy for this one. We'll do this one first. All right. See, it actually holds a lot of decimals. So 0.910, that's the upper R value. Okay, and that's, what you would report in this class on tests, because we always put 3 decimals. All right, hit Control Copy. All right, that goes over here. Okay, the lower one, 0.585. Okay, so that's the confidence interval. So I'm going to double check Lane's guide and see if we got what he got. Let's see. This was 32, I believe. ADH. Yeah. 0.586 and 0.910. Those sound like the same ones. We can double check. I think one of them may be a little bit off. Yeah, one of ours is just a tiny bit off. There's probably a rounding error somewhere in Lane's calculation. I don't think we made a rounding error because we copy-pasted everything. Or perhaps he used the formula instead of the calculators. So slightly different, but almost exactly the same. Okay, so how do you interpret that? Well, let's see here. What we might say... All right, let's see. What is the correlation between a participant's correct number of responses after taking the placebo and their correct number of responses? Okay, well, we can even take a look at and see what this... So, first of all, well, now I'm like losing... Let me close some of these things. No, not that one. I may need all these. All right, so we can actually... look at this graph again. Let's just see what's going on here. Univariate. Let's see. I know model, linear, bivariate. Okay, so looking at the plot there, you can actually see that as DO increases, you know, the placebo scores increase, so do the scores on the D60. So, you know, even looking at this, it's pretty obvious that they're positively correlated. The thing is, you can get a plot like this that looks like things are positively correlated, but still have 0 in your confidence interval, in which case you can't really say that they're correlated. In this case, however, going back to our answer, notice that 0 is not in the confidence interval, and neither is a negative score. Right? You see that? So we can definitely conclude that these two things are correlated. So the way I would, you know, write an answer for this, I would say that as the D0, we're just going to call it that because I forget what it is. Oh, that's the placebo. As the placebo scores increase, so do the D60 scores. All right, and then you could actually put the you know, the confidence interval in here, something like 95% confidence interval on R. Actually, it's rho, and then you could put something like, or actually, we'll use our notation that we've used before. All right, how about 0.585 less than rho less than 0.910. Now, if I was writing, you know, a paper, a scientific paper, this is how I would report this result. Because it tells the direction, so they're positively correlated, right? If these numbers were negative, then that would mean as the placebo scores increase, the D60 scores decrease. But that's not what's going on. Instead, they're positively correlated. So you want to say something like that. You could put the two things are positively correlated. I think this is a little easier for some people to understand. And then over here, because one thing, it avoids jargon, right? And then over here in parentheses, you give people the confidence interval that supports that assertion. So that's the best way to report an answer like this. Okay? All right, now I'm going to just delete this because we're done with that example. All right. And now we're going to work on a new one here. All right, so we're going to be using a new spreadsheet and everything. Okay, so let's see what we have next. All right, so the next one is this, 33. All right, so you can read this one on your own a little bit. So recall that the hypothesis, this is at weapons and aggression. Recall that the hypothesis is that a person can name an aggressive word more quickly if it is preceded by a weapon word, prime, than if it is preceded by a neutral word, prime. You know, obviously written by a psychologist, but that's okay. We use the same methods in biology. All right, the first step in testing this hypothesis is to compute the difference between he's got these two columns, AN and AW. All right, this is the main reason why I wanted to show you guys this, because this is something we haven't really done in Excel before, and I want to show you how to do it. All right, so we're going to go ahead and do that. All right, let's see here. Here we have the guns. All right, so we're going to subtract 2 of these for each individual. Again, we've got one individual and they've got multiple scores for that individual. All right, so theoretically he must have used some sort of randomized design. Now let's see, which ones are we subtracting? AN minus AW. Okay, got to do it the right way. Okay, AN is in C. What you can do is you can set up a new column for this. All right, so we want AN minus AW. All right, so that's going to be the heading, just so we don't lose track of what we're doing. So what you'll do is you write here, you put equal C2, see how it's highlighted, minus B2. Okay, and then that gives you -7. All right, now you don't have to type that over and over. Instead, you hold the control button down and hit C. Notice how there's a little thing going around it. And then you select the cell below that and then drag, hold the cursor down and drag. You gotta depress the cursor to make this happen. See how it turns gray? And then hold the control and hit V. So it actually, you can look at the formula bar here to see as you go to each cell, it's doing the same thing for each cell. So now we have like all the individual ones there, and we can work with that because this is the data that we're interested in. We don't really care about any of that other stuff over there. Okay. So we'll go ahead and look at some of the things he wants to do with this just for practice here. I think you guys can probably handle it from there, but we'll take a look just in case. Oh yeah, there's like a whole lot of things. Okay, would the hypothesis of this study be supported if the difference were positive or if it were negative? Let's just, he tells us positive. I don't want to reread the whole study, so we'll go with that. What is the mean of this difference score? Okay. So now to get the mean, what we need to do, we need to see what's first. Okay, we're starting in cell 2. All right, so we're going to find the mean here. All right, so you just hit equal average G2 to G33. That is one way to do it. Okay, so there's the mean. All right, now let's see what else we want with this one. That looks like what he's got there. He's rounded it off a bit more. What is the standard deviation? So we can do that next. And then we're going to get a 95% confidence interval of the mean difference scores. Okay? All right. Now, this is different than a difference among the means. Remember how I showed you how to do that with past? All right. So that's, you can't do that with past directly. Because we're really working with a single column, okay? So you may remember when I showed you an example up here, we worked with one of these angry mood case studies, and we sort of compared girls and boys, remember that? And then we generated a difference between means. That is not what this question is asking for, all right? So what this question is asking for, you've got a single mean, and we want to generate a confidence interval for that single mean. Okay? All right, so we'll go ahead and do these other things because they're relatively quick, and we can do them in here. All right, so let's see. So we're going to need the standard deviation. I'll go ahead and put that. All right. This is equal to STDEV of G2 to G33. All right. That gives us the standard deviation. All right. Now, we're going to need the degrees of freedom because we're working with a sample. All right. Now, what's the degrees of freedom? So see how there's like 32, right? I think we have, labels in one up here. So there are 32 people. Since we're dealing with a single column here, the degrees of freedom is n minus 1. we've only calculated one standard deviation, so we lose 1 degree of freedom. So this is 32 minus 1 is 31. Those are the degrees of freedom. Now we're going to need a critical value. This is going to be a t critical value. So to get it, what we do is we go over here to Lane's calculator, all right, and we go to the inverse t distribution. All right, let's see here. Inverse t distribution. Now we put in our degrees of freedom that we're interested in. So we have 31. We're going to do a 95% confidence interval, I think. Let me double check and see if that's what he's asking. Yeah, okay. So we need 2.04 is the critical value. All right, so that's the critical value. Okay. So at this point, what we can do is we can just calculate, our upper and lower limits. So we'll put the upper value first. All right. What this is going to be equal to, and you can look at the top of the screen up here, I'm going to be entering the formula here if you want to try this on your own. So we need the mean, which you can see is in cell G34. All right. And we're going to add that to our critical value, which is in G37, okay, times the standard error, which is the standard deviation divided by, so that's G standard deviations is in G35, looks like, right? And that is divided by the square root of n. So this has 32 people. Okay, don't put 31 there. That's degrees of freedom. Okay, all right. That should give us the upper value. Okay, 13.721 is what you would be reporting. Now let's see if Lane has that. I'm just curious. Yeah, he's got the same thing. So you can go ahead and calculate the other one if you want. All right, now let's see what else we have here. This last question here is let's interpret this thing. What does the confidence interval computed in D say about the hypothesis? So for the hypothesis to be true, it has to be positive. To look at, to understand that, you can go back and read the case study. I'm not going to do that. I don't even remember what this is all about. But it has to be positive. You don't see any negative value in there. And you don't have 0 in it either. Therefore, we would say that the hypothesis seems to be correct in this case because 0 is not in there. We definitely have a positive value. Okay, so there's one other question I want to look at. Let's see here, 36. So let's take a look at this one. Okay, again, we're mainly looking at this one. I don't think it's particularly hard. We're mainly looking at this one so we can think a little bit more about how we interpret confidence intervals. So let's see what we're doing here. So we have this student is like studying the ages of couples applying for marriage licenses in his country. All right, and so he's got like a sample of n equals 94 marriage licenses. And he found that 67 of these, the husband was older. Wow, so it looks like the man is usually older. Well, that's what he's asking, Does this support that? Can you say that the man is usually older? And in other words, do we have a big enough sample size to make that assumption? All right, well, to know for sure, we have to generate a confidence interval. Okay. So to get a confidence interval, what we're going to do first is we're going to define the proportion. So that would be 67 divided by 94, right? And then that's a proportion, so you're going to use the same formula we've used for a proportion before. So I won't do that again because it's mostly just plugging in values. All right, what we have here, this is the confidence interval you get. So as you can see, now let's see, for men to be older, this would need to be like 50% or more, wouldn't it? It'd have to be more than 50%, right? And as you can see, the population proportion is somewhere between 70% and 72%. That's actually a pretty narrow 95% confidence interval. I think we can say very strongly that usually, you know, oh, this is, yeah, this is what the older means. Okay, so we can say very strongly that, you know, the husband is usually older in this country. Okay, and with that, we will end this video. I hope this helps you guys with this. If there was a question in here that I didn't work, now that you've seen these, go back and take a look at it, or one that you were having trouble with that I didn't work. Take a look at it again and see if you were able to figure it out. If you still can't figure it out, you can always send me a text message. So the next thing up is the midterm exam. We don't have a separate quiz on this. I'll be asking you questions on the midterm about it. All right, so practice these questions multiple times. That's the key to doing well in the midterm.